So first is EXO. In internal combustion engine, the powertrain of ICE consists of the engine, motor, transmission, and ECU. But in EV, and especially in EXO, they are consist of inverter, motor, and reducer, and they are all housed.
Today we're going to talk about the topic thermal characterization using a calorimeter. Heat affects batteries in multiple ways. As the temperature decreases, ion conductivity drops, and it leads to the decline of battery's efficiency. Or if the temperature increases and SEI starts to decompose over the 60 Celsius maybe, and if it goes continue, thermal runaway happens and it threats the battery's safety. Because of these phenomena, the surface area of active materials decreases and the thermal degradation got even harder. So we have to design optimal thermal model. General calorimeter is only measure temperature. It shows the overcome of phenomenon, and we can't clearly explain the thermal degradation. However, multifunctional calorimeter measure pressure, temperature, and heat generation rate. Especially heat generation rate shows the cause of phenomenon, so we can't perfectly explain the cause of thermal degradation. So we have to use the multifunctional calorimeter. This is the structure of multifunctional calorimeter. First, this is the sensors: pressure sensors, thermocouple, and heat flux sensor. This is simple, just detect the signals. And heat pump, it controls the flow of heat. There are TEM, thermal insulation, heat sinks, and fan. And finally, this is a pressure unit. This is just simple. It helps to apply pressure.
Explain about calibration part. So there are two main reasons why we use this calibration. So first is to change voltage to watt in heat flux sensor. So in heat flux sensor, they show result in voltage, but we want the result in watt. So we need to change voltage to watt by using calibration. And second reason is that we want to get our unknown information by known information, which is an dummy cells heat generation rate. So by using this power equation, we calculate our unknown information. So these two graphs is about calibration's thermal condition and their input and output profile. So if you look at this graph shows how it keeps the temperature conditions isothermally. So it keeps 25C really continuously. And this graph shows that this left axis is about input profile and this right axis is about output profile. So if you look at this red line and blue line, our output profile exactly fits into input profile. So next is about EC measurement. So our reversible heat consists of this term, and we can know our current and temperature by other external information. So what determines reversible heat is that du over dt, which means entropy coefficient. So there are two methods to measure this EC. First is potentiometric, and this measure oscillatory change at varied temperature. So it has high accuracy, but it takes long time. And next is calorimetric, and this measure difference of total heat generation at charge and discharge. And this method is fast, but it measures average value in certain SOC range. So it is relatively inaccurate. So what we use is that HTFDA, which combines time domain and frequency domain. So this temperature domain shows in sine wave, and also voltage is shown in sine wave. So if we process these two time domain data into frequency domain, we can shorten our time and also increase our accuracy. So this is our result, and this means that if we calculate our EC and calibration well, our SIM data, which is an measured and calculated data, fits really well into our experiment data. So this fit in our calculate data and experiment data means that we did our EC measurement and calibration really well. So